Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, what I want to talk about is NOMAD. It's a play on words, so you'll see why it is called NOMAD as the talk progresses. And I want to think of this as some kind of a framework for distributed machine learning. Okay, but majority of the talk I'll be talking about matrix completion, which is a specific problem, and then later towards the end of the talk, I'll show you some ways of why I think it is a framework rather than just a single idea. Okay. So what you're interested in doing in machine learning is obviously you want to build a model, and that's what is the holy grail. But and then the way you measure how well your model does is that you look at something like a loss function. So just think of the loss function as some kind of a sophisticated discrepancy score. Right? So it tells you what target you expect and what target your model actually predicts. And the main sort of, in my mind, the main difference between, say, just optimization versus machine learning is in the fact that your model must generalize to unseen data, right? So this is the whole holy grail, that you have seen some data, you want to build a model, and that model must predict well on some data that you have not seen before. And one way to achieve this is by saying that I'm going to avoid overfitting, and so I'm going to use some kind of a regularization. Okay, so if you put these ingredients together, there is this thing called regularized risk minimization that you end up often doing, and in fact you can show that a vast majority of machine learning methods can be viewed as sort of doing regularized risk minimization. So what you're doing here is that you have some m data points and some corresponding labels. So this is the loss function. So you average the loss function on your data. It's also called the empirical risk. And then you add some kind of a penalty term, which is the regularizer, and lambda is a parameter that trades off between the regularizer and the loss. Right? And so if you do the right amount of trade-off, then you'll get a model. The model parameters are W. Okay, so this is the sort of the general 30,000 feet view of machine learning. Okay, and what I want to concentrate today is on this framework called NOMAD, which is specifically for this kind of a problem, which is collaborative filtering. Okay. By the way, I must mention that just feel free to interrupt me, ask me questions. I don't have to necessarily go through the talk. I'm more interested in having a discussion. Okay, so just any point, feel free to interrupt me. And so this is so the problem that I want to consider is that of collaborative filtering. So I spent my summer at Amazon, and Amazon sells a few million items, as you all know, and of course has a few million users, okay, as again most of you know. And so here are, say, users, and here are items, and you may have some reviews from users, or you may have some purchase history from users, or you may have some interaction of the users and items, right? So you maybe the user looked at this item and then decided quickly went back, and so you can infer that the user doesn't like this item, or maybe he gave a 1-star rating for this item, and then you know that he doesn't like this item, or maybe he gave a 5-star rating and you know that he or she likes this item a lot, and so on and so forth, right? So you have this large amounts of interaction data between users and items, okay, and what you want to ideally predict, and what Amazon would love to predict, is what happens here on items and user pairs where you have not observed interactions. Can I predict ahead what would happen? How would these user item pairs interact? And if the item user pair interaction is going to be positive, should I display this to the user? Say maybe the next time you log into Amazon, it says, hey, this product, I'm sure you will like it. And maybe and if you really do show products that are relevant to the users, actually it does increase user satisfaction. Okay, so the way to think about this is that you have this large matrix, you observe some of the entries of this matrix, and you want to complete the rest of the entries, okay, based on what you have observed. And one way to pose this problem is to say that I'm going to take this matrix which was partially observed, and I'm going to factorize it into two matrices, W and H, such that if I take any row of W and the corresponding column of H, if I take the dot product, that gives me a prediction of that corresponding entry of A. So in other words, I want to factorize A into W or H. Okay. Of course, I can set this up as an optimization problem. Okay, and one way to do this is to say this is the set of all observed entries. Okay, so whatever I have observed. So what I am saying, what the optimization problem says is that for all the observed entries of the matrix, if I take the ith row of W and the jth column of H, if I take a dot product and look at the difference between that and what I observed, then the difference must be small. Okay, so that is the loss. And then of course I want to add a regularizer, and one way to regularize is to just simply regularize the individual rows of W or H. Right? So if I add this regularizer, and then there's a lambda parameter. So again, this is an example of a regularized risk minimization problem.
Are you going to talk about the problem of choosing K in this?
No, I'm not. So I'm just going to assume that you have a God-given K in this case. Okay. So, but yes, there are. So I'm not going to talk as much about the modeling aspects of the problem as I'm going to concentrate on the optimization aspects of the problem. Okay. So.
But in general, I believe you can choose K implementation.
Yeah, usually you choose something. I mean, you choose something reasonably between 10 and 100, something like that. And what I will show is that the algorithm that we actually have is fairly independent of K. Okay, so it doesn't really matter what K you select, as long as the K is reasonable, it will give you an answer within the similar time bounds. Okay. So any other questions so far? Good. Okay. So now sort of let's enter into the more interesting part of the talk. So this is all about background. So now one way, I mean of course there are many different ways in which you could solve this problem, but here is one possible way in which you could solve this problem, and it's kind of popular, is you could use a stochastic approximation to the objective function and then try to solve the, do a stochastic gradient descent. So the way you do this is that you would take your objective function, you would approximate it with this one-step objective function. So here, if you remember, there was a summation in the objective function here. This was a summation over all observed entries, and now you simply say I'm just going to not do the summation. I'm just going to look at this one-step objective function. Okay. Now I'm going to pretend that that is all that I know about, or that's all that I care about. Now if you pretend that way, then you can easily compute the gradient of this approximate objective function. So the gradient looks like this. This is high school math. You can do this. So this is the gradient with respect to W, and that's the gradient with respect to H. Okay. And now you can do a stochastic update. Okay. So the stochastic update simply says I'm going to update W by using the ith row of W, by using the ith row of the previous value minus eta times the gradient. Okay. This looks very sort of unassuming, and there's nothing fancy going on here, but I want to point you to one particular very, very important observation in the slide. Okay. So the main observation here is that when I want to update the ith row of W, and I want to update it with respect to Aij, the ijth observed entry of the matrix, then I only need 3 pieces of information. Okay, so what are the 3 pieces of information? I need to know the previous value of W, so the ith row, I need Wi. I need Hj, okay, so the corresponding row in H, and I need to know the value of Aij. Okay, so if I have these 3 pieces of information, then I'm done. I can do this update. Okay. What is remarkable about this updates is that this does not depend on anything else. It doesn't depend on the state of what is happening to the rest of the W's. It doesn't depend on what is happening to the rest of the H. As long as I have these 3 pieces of information, Wi, Aij, and Hj, I can do this update. Okay, so it's sort of very nicely factorizing in some sense. So then the obvious question is that if you have a very large problem, okay, and say if you are Amazon and you have the Amazon scale problem, or you own IMDb, which Amazon does, and again you have a few million users and a few million, well not a few million, but a few hundreds of thousands of movies, right, and then you want to factorize the ratings from there, then how do you do this? Okay. Here I want to point out, because there was this question earlier about, okay, what is big data, and why should we care about big data? type question. So here really it is important to use all features. It's very important to use all purchase history from all the users. You do see a gain. That's number one. Number two, it's not clear in this setting how to do subsampling. Right? What does it mean to subsample? Right? I have a matrix. I have data which is on a matrix, and how do I do any kind of subsampling on this matrix? Right? And even if I do subsampling, what sort of information am I losing in that process? Okay, so therefore you do want to use the entire data.
So what is the sparsity of data
that you all the results that I'm going to present are on public datasets, and even there the data is very sparse. And in general, you would expect that the data is extremely sparse, because obviously if you are selling 2 million items, users are not going to look at 2 million items. It will be very small. I mean, I don't know I don't even remember the exact numbers on IMDb, but it is fairly sparse. Okay. Yep. You can enforce other regularizers. So here right now, okay, yeah, that's a good point. I didn't mention this. But what I'm going to talk about allows you to change this loss function and this regularizer to other regularizers. So that's fairly easy. Okay? But we are going to do the simplest case because I just want to convey the basic ideas. Okay? So other questions? Okay, good. So now if you want to sort of distribute this computation across multiple machines, then how are you going to do this? Here is a potential possibility of distributing these updates across multiple machines, and this is a paper from KDD 2011. The idea here by Gemula, and the idea here is that you take your entire matrix, okay, of observed ratings, and you divide them, say here in this case, into 4 machines. Okay, so this basically the one machine gets the entire red block, the second machine gets the entire green block, the third one gets the blue one, and then the gray one, and so on. Okay, so each machine owns this stripe of the data and so on, and the crosses represent non-zero entries. Okay, so which means that all this part of the matrix is stored in one machine, this part of the matrix is stored in the other machine, and these are all the non-zero entries in this part. Okay, and what you do is you start with your parameters also distributed in this way. So what you do, and so each machine here, say this machine will get this block of W parameters, okay, and it will get the corresponding block here of the H parameters. Okay, so this machine has this W and that H. The third machine has this set of W's and that set of H, and so on and so forth. Okay. Now what this means is that for any entry Aij here, okay, you have enough information to perform stochastic gradient updates. Remember, I told you in the previous slide that to do an update to Wi, you only need to know Aij, Wi, and Hj. Okay, so which means that if I choose any non-zero entry here, so let's say if I choose this entry, in order to perform an update to the corresponding Wi and corresponding Hj, I have all the information on this machine. Okay, and the same thing goes. So any non-zero entry in this part of the matrix, I can perform an update. On any non-zero entry on this part of the matrix in the third machine, I can perform an update, and so on and so forth. Okay. Now what the scheme does is initially it does this kind of a decomposition of the parameters, sends it to different machines, perform an update, and once the update is once you sort of sample sufficiently in each part, you synchronize and you communicate. So what does communication do? You exchange blocks of H. Okay, so if you pay attention, here there was red, green, blue, and brown, and now they have exchanged blocks. Right? So now this machine has brown, and this one has red, and this one has green, and this one has. Sorry? Okay. So what you do is that initially you start with this assignment of parameters. Right? So this guy. So let's be very concrete, and let's say the first machine gets the first 4 columns of H. The second machine gets the next 4, and so on and so forth. After you have done your updates, you synchronize and you communicate. So how do you communicate? Now the first machine will send the columns of H to the second guy. The second guy will send it to the third one, and so on and so forth. Okay. So now the first machine has all the information that it needs to perform updates with respect to these set of non-zero entries, clear? And so on and so forth. Okay. Of course, you won't do it sequentially, so you don't do machine 1 sends to machine 2, machine 2 sends to machine 3. You just do it randomly. So you pick a random machine and then you send it to somebody. Sorry? Yeah, but the communication is not stochastic, right? So the communication you have a pattern and you update. Okay? Yep.
When does the heads update happen?
Sorry?
When does the heads update happen? So far we are doing only W updates, right?
No, we are doing updating both W's and H's, right? So they are happening simultaneously, and then you keep on updating both W and H. So basically, the first machine will update this part of H and this part of W, and then again you'll synchronize, you'll communicate. Okay. Now the problem with this synchronize communicate paradigm, which is very popular, is that, or maybe I should first talk about why this is a good paradigm. First of all, this is a good paradigm because the updates are decoupled, right? It's sort of the neat observation is that to update Wi and Ha, you just need Aij, Wi, Ha. These three pieces of information are needed. So the updates are decoupled. That's a nice observation. So it's very easy to parallelize. Conceptually, it's pretty good. And because of this synchronize communicate pattern, you can easily do a MapReduce, right? So all you have to do is put it on your favorite MapReduce platform, Hadoop, MPI, whatnot, and you're done. But what is the bad part about this? So in my mind, one of the sort of biggest drawbacks here is that communication and computation are interleaved. So when you are doing communication, you're not computing, and when you're computing, you're not communicating. So if you look at the network, if you look at the load on the hardware, you're hammering the CPU, the network is idle. You're hammering the network, the CPU is essentially idle. Okay. So the one question is that can we keep both of them simultaneously busy? Okay, this is one. But also there's a bigger meta question, probably we'll do some of this discussion when we have the panel discussion in the afternoon, but I just want to leave this thought with you, is that in some sense MapReduce is essentially the wrong paradigm for machine learning for the following reason. As the data size grows, okay, you want to add more and more machines so that you can solve a larger and larger problem. Okay. What happens in MapReduce is that as the number of machines grows, the burden of synchronization grows. Okay, and eventually what will happen is that you will get to a point where you will be spending all your time on synchronization and communication and not so much on computation. And this is kind of counterproductive because you really are doing the wrong thing. As the data size grows, you should be spending your time on computing, not on communicating.
So I'm not sure I understood your argument. There is a MapReduce as a general abstraction.
Mm-hmm.
There is a computation to do.
Mm-hmm.
The two could have very different characteristics. Are you making a claim about the two or about MapReduce?
No, I'm talking about MapReduce. So, okay, what I'm talking about is this notion that when you communicate, okay, and you have to synchronize. Okay, so I'm talking about synchronous bulk synchronization at every step that MapReduce requires. So I'm talking about MapReduce, and of course, the concrete implementation Hadoop, of course, suffers from it because.
You could do a MapReduce in a style where you don't have to synchronize globally. You've got a tree structure, and as you go up the tree, locally you combine and reduce and so on. You could do things like that.
So I mean, there are clearly engineering solutions to this whole problem. But the argument that I'm making is that synchronization is kind of counterproductive as you go to larger and larger number of machines, because first of all you have to wait for all the machines to finish their jobs. So there is this thing called the curse of the last reducer. The second thing is that you spend a lot of time on synchronizing, and so your network costs go higher, and so it's sort of as the problem size increases, you're spending all your time on the network, which is really a bad thing.
Well, two things. So one is that you're having a CPU, but these computations seem sparse, so you're really still bound by how quickly your memory system can feed the CPU, not really how
Yeah, but I mean, a memory system, a memory bus on your machine is significantly faster than any interconnect that you can get, even on an infinity band. Yeah.
The other thing is this overlapping communication and computation. It's been researched to death almost in HPC.
Yeah.
And that leads to very tightly coupled systems, which is good in some sense, like I can do a lot of this. And then you have MapReduce, which allows you to dynamically move machines and
Yeah. Yeah.
fault tolerance.
Yeah. Yeah.
So are you arguing for one over the other?
No, I mean, I'm saying that you can have the best of both worlds. So I'll talk about the framework that we are developing, and you can actually get both for, I mean, our current implementation doesn't support fault tolerance, but that's not because the algorithm cannot be made fault tolerant. It's because we just don't have the bandwidth to do the fault tolerance.
So actually continuing with that, communication and computation, so this problem actually has typically been solved without resorting to overcoupling. It's basically by over-partitioning. So if you have 4 CPUs, if you basically had, rather than splitting your WI edge into 4, you had split them into 16 and let the machine schedule essentially.
I'll show you that. Actually, CJ Lin has a very nice paper on that, and we'll show that actually we do better than that. Okay, and again, coming back to your comment about the memory subsystem, we do have to design it carefully, right? So that that you see, it's very important to ensure that your updates are local. You are able to take advantage of memory locality, and cache misses are reduced. All that stuff is important, and it does make a difference, and we'll talk about some of that. Was there a comment somewhere? Okay, good. I'm glad that it's starting a discussion. Okay, so we'll have more in the panel discussion. Okay, so our answer to this problem is NOMAD. Okay, so how does NOMAD work? It does the same kind of partitioning as before. Okay, so you partition your data in exactly the same way. So you stripe your data, and these shards of the data are fed to each machine, and then you shard your parameters in exactly as before. Okay, and you start off with this set of parameters. Okay, but now comes the difference. Okay, so each machine starts. So let's say that this first machine starts updating all these parameters. The second machine starts updating these parameters, and so on. So everything is as before. But now we make this change. At some point randomly in time, okay, machine 1 will randomly pick a column of H. Okay, and it will randomly pick a neighbor, and it will decide to transmit this column of H to this neighbor. Okay, so in this case, machine 1 will say, I'm going to pick the second column, and I'm going to transmit it to the fourth machine. Okay, completely asynchronously, no synchronization. Okay, and the fourth machine, when it receives that column, now has enough information such that any non-zero entry in this part of the matrix, it is able to perform updates with respect to that. Okay, so now the fourth machine can perform updates on any of these parts of the matrix. Okay.
So there's enough memory pre-allocated at every row.
Sorry.
There's enough memory pre-allocated.
No, there is a queue. So there is a receiving thread, and the receiving thread keeps on receiving parameter updates. These parameters are usually small. So if you have a scalable allocator, you can handle, so we do pre-allocate the blocks, and then we use a scalable allocator inside the blocks.
Two comments. I think what he was trying to say was, you have space for 4 columns, and that's all you can afford. Then the 5th column is something you cannot possibly keep.
Yeah, so we can do that. So one of the things I'll address that question. Okay.
So my comment is different. So you said you randomly pick a neighbor, but in a real cluster, there is such a thing as distances and congestion. So
Yes.
this randomly picking a neighbor, how good is it as opposed to knowing, like say you have a gray code and you shift more.
Hold your horses. We're getting there. Okay, so there's more. I mean, I'm giving you the simplest vanilla scheme, and there's more to it. Okay, other questions? Okay, so is the basic scheme kind of clear, that each machine is working on a set of parameters and a part of the matrix. You randomly take one of the parameters or one row of the parameter, and you pick a random matrix, a random machine, and you send the parameter over to that machine. You communicate. Okay, and on each machine, whichever set of parameters that you own you perform updates on them. Okay, and then sorry.
That's done in parallel.
Yeah. So you have threads on each machine, and the threads are working on the parameters that you own, and then and then you randomly pick a parameter and you transmit. Okay. Now, when I say random, okay, there are many things that you can do on top of this. Okay. So the first thing that you can do, and this is what we do, is you can send a payload along with each message. Okay. So whenever you receive a column from some other machine, you receive a payload. Okay. So the payload can, for instance, include things like how busy is this machine, right? Or how much, say memory capacity it still has, or how much, how many updates has it performed on its set of data that it has. Now you can use that information to tailor your random picking of columns. So for instance, a very simple example of doing it randomly but yet respecting the load of each machine is to say that if the number of parameter updates or if the capacity of the machine is low, then the probability that I will select that machine as a random neighbor to send my columns to is low. So this is how you do dynamic load balancing. So on the fly, along with the messages, you send a payload. The payload is usually very small. You can pack an integer or two along with this, and then the other machine decodes the message, and then you get to know how much load there is. So what this means is that if you have machines with different capacities, so you don't have to have a server rack, right, all with identical machines. You can have machines with different capacities, and you can actually decide on the fly based on their capacity or their load, you can load balance. Okay, so that is one thing.
Why are you dealing rather than stealing?
Sorry?
Why are you dealing rather than stealing?
Can you make that more explicit?
It's like you're pushing, it's not pulling.
You can do either, right? We do pushing just because you are anyway communicating, so you might as well add a payload to it.
It's a huge difference because the puller knows that he's got nothing else to do, so he can use some of his cycles to go get work and work on it. But the pusher doesn't generally.
But the pusher knows when it's done, when the work on that parameter is a certain way.
Yeah.
So that's the motivation.
That's the motivation that, I'm done with my parameter, now I have to figure out where to push it onto the network, right? So there is both models have their advantages and disadvantages. With the pusher model, the disadvantage is that in some sense you have slightly older information because, the machine tells you that my current load is this, right? And you use that information to figure out how much load, you don't know exactly what the load right now is, you know probably a few microseconds before. So in the meanwhile, if all the other machines decide to send data to this guy just because he's not loaded as much, you will, you can have some of those network spikes. Okay, but
The problem is it does not scale.
it
If you go to 100,000 machines, keeping all of this information is a problem at every node.
no, because this parameter when this comes, every time there is a fixed load. So the payload is not scaling with the number of machines. So I am just going to push to you the information about here is a parameter for you and here is my load. So then all you have to do is you have to say, okay, now I know I have the latest information from this machine, I know what his load is. Of course there's a little bit of delay in the load, but that's it. Okay, so it does not scale with it scales pretty well.
The one issue I find with this scheme is that your now communication is lots of small messages, and it
Okay.
basically latency bound. Therefore, it has to be asynchronous. It cannot never be.
Okay. So there's another. Okay, so there's a lot of things that we do under the hood. One of the things that we do under the hood is that you accumulate messages. So you accumulate messages to get. So usually, if say your k is 100 and plus an integer, so it's like about. So if you accumulate about 10 to 15 messages, you will have enough on the buffer that it makes it worthwhile to communicate.
So when the first machine decides to set a column to another machine, it's actually done with that column. So it decides that okay, now I'm done with this column. Now I'm
Yeah, but then it will come back. The columns are circulating. So now I want to tell you why it's called NOMAD. Kind of, if you have been paying attention, it is obvious because these parameters are nomadic. They are wandering around in the network. right? So the W's are static, the H is nomadic. Okay, so they wander around nomadically in the network. No, I'm fine. I don't have to. Yeah, I will end whenever I want and whenever everybody is yeah, and when Bruce is. So if a machine falls behind, you get this information in the payload, right? So you get this information in the payload saying that I am overloaded right now, don't send me messages. And then the other machines will respect that.
Yeah, that part of the computation cannot be, so it's still sort of, some part of the computation still cannot be done because.
So there are other ways to do, again, we don't do it, but the algorithm does not preclude you from actually dynamically load balancing the data as well. So you could at some point of time say that, okay, this machine is overloaded. So I didn't talk about the fault tolerant aspects. So there are two parts to that. So the fault tolerance aspect to this is that you actually can have, I can take this offline. We don't have an implementation yet, but it is possible to do fault tolerance. And also it is possible to load balance on the fly. So there is nothing which prevents you from load balancing the data, but you don't want to do it in general because you want to take the computation to the data, you don't want to take the data to the computation, right? The other way around, if you have a terabyte of data, moving it even inside your data center is hard.
So we addressed this earlier, but it was still not very clear. So you said every node and every message has a payload, which is how busy a particular machine is. So every machine actually has a list of all these payloads and it needs to keep track of every other, how busy every other machine is. So does this not?
No, this is just an array of integers of the number of machines, right? If you don't even have like an array, I mean, let's say what's your number of machines going to grow to 10,000, right? I mean, if you have a reasonable data center, right? So you have an array of 10,000 integers.
It's possible that one machine is free and everybody decides to send messages to that machine.
So that's exactly why you don't do it. You don't do it by looking at the machine. So you don't deterministically send your message to the machine which has the lowest which has the highest capacity. You have a sampling scheme, but the sampling scheme is weighted towards favoring that machine. But that doesn't mean that that's exactly why you so there is a higher probability that if I have capacity I will receive messages, but does not mean that everybody will jump on me and give me messages if I have capacity.
So is there maybe a possibility of centralizing this thing?
No, you absolutely don't want to centralize. You absolutely don't want to centralize. You will not, see, the reason you don't want to centralize is you don't want a single point of failure. Okay. No, the initialization is here, right? So this is the initialization. So, it's random, right? So there is the W's and the H's are there is you sample from a random distribution. Okay.
So is there an algorithmic assumption that you only communicate with those who are already communicated to you?
No.
So then how do I know the place where I go to? If it has not communicated to me, how do I know that my data?
So okay, there is so I'm assuming that we are not doing, again in our code we don't do discovery. So we assume that you are aware. So you are aware of the topology of the network, right? So but there is nothing which prevents us from adding a discovery layer on top of it, right? I mean, you could go through something like Zookeeper and sort of say, okay, tell me what's happened.
Not if you want performance. So
Sure.
I don't know where you are. Are you in performance? Are you fault tolerance? What's going to the design space of these algorithms are you after?
So I am after the following. I am after having not having a single point of failure. I am after not having a synchronous communication, and then all the rest that I talked about, discovery, fault tolerance, moving of data, all of this can be added on, but we don't do it because we are not systems people. I mean, we sort of, I mean, it's me, Inderjit, and a couple of our students, right? So we only have that much capacity. It's okay if you send it back because there is still information because. Sorry? Yeah, because you have changed the column, right? So you are constantly changing the column. So even if there is a small probability that I send it back to you, you still have new information. Okay. I mean, there are other things that you can do. Again, the payload, you can make it longer and say who has not received this column. All those things are possible, right? I mean, but basically, this is bread and butter. You can add everything on top of it, right? You can make a whole meal out of it, but I hope, and this is one of our hopes, we have the code is on Bitbucket. We'll release it. I mean, there's a version that is already released, but the code is on Bitbucket. You want to hack on it? Welcome. We'll give you a Bitbucket access, and you are happy. I mean, you're more than welcome to hack on the code.
You're distributing. So if there's a matrix, then you're distributing one of those in blocks and the other one by rows.
Mm-hmm.
Sorry,
are you talking of the distributing the parameters, or are you talking of distributing the data?
The rows stay constant.
Yeah, here. So here the row parameters stay constant, and the column parameters migrate.
Is there a reason why?
It doesn't matter. It's symmetric. It's completely symmetric. You could have migrated the columns. You could have kept the columns symmetric, static, and the rows. The reason we do it for matrix factorization is usually the number of row parameters is much larger than the number of column parameters, because the number of movies is in hundreds of thousands, number of users is in millions. Right? So, questions? Okay, so where are we with things? Okay, so now I just want to quickly also talk a little bit about other things that people have been doing. Was there a question there? Okay, so I also want to quickly mention what other possibilities or other ways in which you could have solved the same problem of interleaving of doing simultaneous computation and communication. So here is one proposal called DSGD++. This is also by Gemula's group, and this is a recent paper in ICDM. And here what you do is that you instead of exchanging an entire block, you divide the block into two. You are doing updates on one half of the block while you are communicating the other half of the block, right? And then you do this. One of the problems with this is that sort of, if you are doing real parallelism, you really want to break down your units of work into the smallest units of work that you can, so that you can do better task stealing and better sort of scheduling on your machines. Here, because your tasks are sort of still block size, there are some issues associated with it. I can talk to you more about this offline on why this still does not, I mean, it resolves some of the problems, but not all the problems. And of course, it still requires synchronization after every block is updated. Okay. So this is the second scheme to solve this. This is over partitioning. So this is from CJ Lin's group. Was this Rex's best paper award? Yeah, I have lost track of your best paper awards by now. But yeah, this is a best paper award at Rex's, and this does over partitioning. So basically, you take your data, you over partition it, and then there is a thread manager. So the thread manager allocates work to each thread, and then what you do is that whenever a thread is finished with a block, it goes back to the thread manager and says, give me a different block. Because there are more blocks than there are threads, there is always work for each thread. Okay, so that is the way you do this. But it is not entirely clear. I mean, maybe you have ideas on how to extend it to the multi-machine case, but it is not immediately obvious how to do this, in a multi-machine case. Sorry? But there is I mean, I don't know how to not have a central thread manager, right? So you need to have. Yeah, but then the blocks still need to be, there has to be somebody who allocates the blocks, and there still have to be some scheduling, okay? Block. Mm-hmm. I see. So yeah, I mean so there is sort of distributed allocation. Yeah. So there is actually, our fault tolerance scheme is based on the same idea, that there is an owner for each column. And if you do not see the column back in your network, you revive the column again, and then you circulate a second version of the column. So you can do versioning, you can do all kinds of things in our scheme too. Okay, and then sort of this is what NOMAD does. It sort of finds the finest granularity of work that you can find in this case, which is single column, and then it circulates these columns. Okay, and of course, I talked about load balancing and so on.
So, maybe are you going to talk about the emergence guarantees?
Okay, so that's a question that I think we have to address. We haven't started addressing it yet. One of the issues that we have is that, sort of the first step towards convergence guarantees is what kind of assumptions are reasonable to make in order to come up with a convergence proof, right? So should I assume that each machine will communicate with each other in a fixed, these are just some ideas on how to do this. I have some possible indications on how to do it, but no, we don't have a convergence guarantees. Sorry?
Are you talking about deterministic guarantees or expected guarantees?
You can only do expected guarantees, right?
It depends, right? For example, if you're talking about this thing, right? Let's say in every n communication, at least each machine is a varied once kind of thing, right? Each machine communicates to every other machine at least once.
Yes.
So obviously go for deterministic guarantees with a delayed parameter, which kind of slows down and kind of slows down over convergence, right? Inverse case.
But the asynchronicity is because the problem is because you're selecting a random neighbor, right? So there are issues. It's not a straightforward algorithm to analyze to simply say, okay, here is how the communication pattern flows, and that's how I know exactly where each piece of information is. So it's much easier for instance, it's much easier to analyze DSGD as compared to NOMAD.
So how do you deal with the fact that in a real life situation the number of users is going to be dynamic and the number of movies is also going to increase and that?
Actually, you can add users to the system. There is nothing which prevents you from doing that, but then you'll have to solve this problem of discovery. So you can add a new machine to the system, but then you'll have to inject the information about the existence of that machine into other machines so that they know that this is another candidate for sending. Okay. So I'll show you some experiments, and I'm very excited by the experiments. Okay. So this is just 3 data sets publicly available. Okay. So there's Netflix, which is been beaten to death, and then there's Yahoo Music, which has about 252 million non-zeros, and then there's HugeWiki, which has 50 million rows, 40,000 columns, and it has 2.7 gigabytes, 2.7 giga non-zeros. Okay. Yeah, and there are versions available, but unfortunately Netflix withdrew the actual data set. Okay, so we are using some illegal data set. Okay, I'm on video. Okay, so here is what happens on a single machine. So this is FPSGD ***, which is the over partitioning scheme. CCD++ is a column coordinate descent solver that was developed by Inderjit's group, and then there is NOMAD, our algorithm, and you can see that we start reducing the test RMSE extremely fast, even on a single machine, even with over partitioning. And the other thing I must add here is that FPSGD *** does a lot of tricks by using the floating point operation. So they pack 4 operations into one, and they use the SSE instruction set of the Intel machines to do their updates much faster. We don't do any of those tricks. This is plain simple vanilla C++ code.
So there are these algorithms which do this kind of clustering over the items and clustering over the.
Yeah, no, we don't do. We can do any number of pre-processing steps. We can do.
No,
so
what I'm guessing is, I guess the question is this, right? If you do this clustering, right, and then you take this per cluster and do some sort of trivial parallelization over there, right? Where really you're again, it's kind of fit into the kind of framework that is talking about, right? You do this clustering over users per item statement. People do that.
Yeah.
And then try some of the parallelization approaches which Indrajit talked about. Do you really want to go, because the thing with the asynchronous thing is that
but they are not orthogonal. They are actually parallel, right? There is nothing which says that you can't do the initial clustering and then still do the communication the way we are doing it.
The point I'm trying to make is that in that case, because probably the number of synchronization steps become reduced drastically,
Yes, but see the
So
thing.
will it be the case that computation starts dominating communication a lot, and then you don't really
No, but
care about
your data is distributed. If your data is distributed, your data is not fitting on a single machine. You have no choice.
The assumption is that you can't move around the data. That's
No, you never want to move the
never
data
want
if you can. If you can, you never want to move around the data. Okay, because you always want to take your communication, your computation to the data. Okay, so this is what happens on Netflix, on Yahoo, and on HugeWiki. But I want to show you something that's very interesting. Okay, so this is sort of to show that we do reduce the test RMSE reasonably fast. But here is what happens when you look at scaling as a function of number of cores. Okay, so you keep on increasing the number of cores, and you want to see how the scaling goes. And instead of plotting one of these, single line plots where you show, okay, when you have 4 cores, what is the speed up? When you have 8 cores, what is the speed up? And so on. We decide to give you the full picture of what is happening. So here you take the seconds into number of cores. In other words, this is the total computation that you're expending, right? So if you spend 1 second on 4 cores, then this is like 4. Okay, so and if you spend 4 seconds on 1 core, that's the same equivalent. And you can see if you're scaling linearly, then these lines should more or less overlap. Okay, of course, which you can see happens here in Netflix. Now something interesting happens in the other data sets. Okay, as the number of cores increases, you actually see that you speed up. So this is 4 cores, and this is 32 cores. Okay, the reason for this is that your data is now becoming divided into finer and finer grains, and you're exchanging information much faster than before. Okay, so because of that, you get more. You are updating with respect to fresher information, and actually you speed up. Okay, so this is, I call this, you get this super linear speed up for the price of a linear computation. Okay, so as you have 4 cores, go to 32 cores, you actually do more than 8 times faster. So you actually converge something like 10, 15 times faster. Okay, and this is something that's a cute feature of this algorithm. Of course, this doesn't happen. So there is also, there's always no free lunch, right? So if you keep on further and further subdividing the data, then the number of units becomes so small that you don't get any information from that. So that's what you see here in HugeWiki. So starting with 4, you go to 8, you're still okay, but when you go to like 30, then you start actually slowing down a little bit. Okay, this is what happens on a HPC cluster. Okay, and again, we are significantly faster, but I'll show you more sort of interesting results. So the same thing on HPC, but okay. So this is the sort of, this should interest the systems people in the audience. Okay, so this is AWS, Amazon Web Service, sort of one of the crappiest machines that you can get. Okay, interconnect is bad. It's like less than 1 gigabyte per second. Throughput is not sustained properly. And anyway, and there are 4 cores. Okay, and the way we run these algorithms is, because NOMAD requires 1 thread for receiving and 1 thread for sending, we only use 2 threads for computation. Okay, 2 threads are constantly computing, 2 threads are constantly involved in network. All the other algorithms, DSGD and CCD++, all 4 cores are computing. Okay, so they have a much bigger advantage than us, just because they are doing twice as many updates as us. Okay, and look at the results. This is crappy commodity hardware. Okay, not on a HPC cluster with a beautiful interconnect, infinity band connect. Okay, so with just two threads, 2 cores, versus every other algorithm using 4 cores. Okay, so here is what I think of this as an interesting other plot, which is, you're always interested in knowing what happens if, suppose, as my data set grows, if I keep the amount of computation per machine fixed, but I increase the number of data sets, the number of machines. Okay, so the amount of work per machine is fixed, but the number of machines grows. Okay, then how do I scale? And this is scaling behavior. This is sort of what I think is really what you want in when you're deploying such systems. You want to know, I have 10 times more data, here are 10 times more machines. Tell me how do I scale now, right? And you see this scaling. Okay. So this is for 4 machines, the same, now that you have 4 times more data, so now you have 16 machines, and then you have 8 times more data, and now you have 32 machines. Okay, and you see why synchronization is bad. Okay, both DSGD and CCD++ have to synchronize, we don't have to synchronize. Okay, and this is just to show you that we are fairly independent of the regularization parameter, and then there's the other set of experiments to show you that whatever value of, so there was a question before about the value of k, doesn't seem to really matter in terms of convergence of our algorithm. You still get, I mean, of course, there is some difference, right, between k 10 to 100, but more or less your, your convergence guarantees are not affected. Okay.
So the other algorithms you showed, they had the same objective function?
Yeah, everything is the same. Yeah, except that you have to remember that because it's a non-convex objective function, optimizers will go to different solutions. Okay. Yeah.
Even if you start from the same initial, in this case, if you start.
Yeah. It's a very, so this is where something that's very important. Actually, these experiments are very carefully done, extremely carefully done to ensure that they all start from the same starting point. They all have the same, they all have the same sort of objective function. They are scaling. I mean, so everything is held constant. Like it's.
Saying that the final solution ended up different.
Yes, because it's non-convex. So the objective function is non-convex. So you will end up with different solution. And then I just want to make one more comment, which is that we spent a lot of time on GraphLab, and I think between Inderjit's students, my students, and us, we spent maybe like a month of our man-month of effort, and we couldn't get GraphLab to converge on these problems. Eventually, we did get it to converge, but the solution was really, really bad, and the time was so bad that we couldn't plot it on the same plots. We have we have sent a lot of emails back and forth. I think we have exchanged 60 emails with the GraphLab guys, and it's not entirely clear. I mean, we have given them access to our clusters. They have looked at it, and
they have metrics separation algorithm.
Yes.
So it's their algorithm.
Yeah. So it's the same algorithm, same data set, same hardware.
What asynchronous? They have different asynchronous.
They have a different notion of asynchronicity. They actually acquire network logs. We can talk about this offline. Okay, and just 2 minutes, can I? Okay, so I'll just show you why I think of this as a framework rather than just as a matrix factorization one-off thing. Okay, so question is that can you extend this to a larger class of problems? Okay, and here is the general matrix, the regularized risk minimization problem. I'm just going to do a series of transformations, and I'll show you that you can rewrite this problem in the same bilinear form that you saw for matrix factorization. Okay, so the first thing I'm going to do is introduce a new parameter ui. Okay, and then now I can write it this way. Okay, now I take this constraint into the objective function by using an alpha I, okay, which is a dual variable. So I have to do a min with respect to my primal and max with respect to my dual. Because the problem is convex, usually if doing regularized risk minimization, say logistic regression, SVM type things, I can exchange the max and the min. Okay, so this is fine. Now I can push the minimization with respect to u inside. Okay, so I get this. Now all I have to do is to realize that this is nothing but the dual, differential dual of L of the loss, and I get this. Now I get a saddle point problem, and now look at the structure of the saddle point problem, and you'll realize that it has exactly the form that you need. Basically, it has the form that each term, see this term depends only on W, okay, that term depends only on alpha, and the interaction term is only a linear product on alpha and W. Okay, so which means that if I look at this stochastic, so I can rewrite it in this way, and the stochastic gradients look like this. Now when I need to update a coordinate of W, all I need is a coordinate of my data and the corresponding alpha. Okay, and I get exactly the same format, and I can do regularized risk minimization. And it turns out that we have some preliminary experiments. It doesn't converge as fast as SGD or dual coordinate descent. We are working on it, but it does converge, and we do get reasonable performance. It's not very good yet. We're still working on tuning parameters, but I just want to give you a feel. And that's why I think that this is a much more general framework. This is sort of potentially a new way of doing a lot of machine learning algorithms. So this is logistic regression using the same setting. Okay. So the code, so NOMAD is available on arXiv. There's a code. The code is available from Yun's homepage, and the paper and code for RERM are hopefully coming soon. These are my co-authors. There's Inderjit, of course, who's here, and then there's Hoikun Yun. He's my student, and Shang Fu and Cho are Inderjit's students, and Shin Matsushima is an assistant professor at University of Tokyo who never sleeps. Because he can always respond to my Skype messages any time of the day or night. And if you have any questions, I'm glad to take them.
Just a quick question. How is this implemented?
C++. MPI. Yeah.
How many lines of code?
Roughly maybe 1,000, 1,500. It's not a lot. Yeah.
So if you're using the MPI, then why do you dedicate threads? Because just been using the synchronous MPI.
Yeah, we could. I mean, we just it just makes life easier, because when you receive a column, then it goes into a queue, and we can manage the queue ourselves. So that's all. I mean, it's just, you could call it laziness in programming. With MPI, the problem is that you would have to receive a notification, and then a thread has to go and pull the data from the buffer. Here, you just have a thread that is dedicated to receiving and sending. Other questions?
I guess we'll take them offline. We're already
Yeah.
running.
Okay.